All right, we're back. We're on page 4 of note 17 of Calc AB, talking about accumulation functions and therefore also the second fundamental theorem, which is how you find the derivative of an accumulation function. So let's see how we can do this problem. So this problem feels, I do not recognize that integrand at all. This feels like it's going to be a calculator problem. And I'm basing that pretty much strictly on the fact that I have no clue what I would do with this if I didn't have a calculator, right? Like, can I find any values of that? I guess at t equals 0, I could potentially deal with it. Otherwise, like, what are you going to do? So I think this is going to be a calculator problem. Well, and also I could have just read the problem. It says, use your calculator to estimate the average rate of change. Average rate of change, algebra 1 slope. Always got to think that. So as soon as you see it, average rate of change, you should say algebra 1 slope. I'm going to put an exclamation point because that's what it is. All right, so we're trying to find it on 1 to 3. So that's going to be f of 3 minus f of 1 over 3 minus 1. Okay, so that's the algebra 1 slope. Now let's look at this because, and I'll explain why we're looking at it in a second. So if we actually do it, it'll be 0 to 3 of the square root of 1 plus cosine of the square root of t. This is annoying to write. dt minus. Also, I got to move things down. Hold on. Let's move down here. Okay, so it's that, and then it's going to be the integral from 0 to 1 of the square root of 1 plus the cosine of the square root of t. Oh, I see. There was, like, in my brain, there was something wrong with this. I forgot to put parentheses around the square root of t. Then I just copied it. And as I was copying it, I was like, that doesn't feel right. Okay, over 2. So one of the things you can do here, you don't need to do this, but I think it's a great idea. Because you're doing the integral from 0 to 3 and the integral from 0 to 1, that's actually just going to give you, and the way that I often handle these is I'll draw a line segment. Right, so I have a line, and I'm going to label this as 0 to 3. And then I'll draw, so that's for the first integral. And then for the second one, I'm going to draw another one and just label this from 0 to 1. So if I go from 0 to 3 and I subtract 0 to 1, you can actually just lay it out and look at the bounds to figure out what integral we're left with. So we're actually left with the integral from 1 to 3. So this thing that we've written so far, now I'm going to move this out of the way. The integral that we've written so far, actually before we grab a calculator, can be reduced down to the integral from 1 to 3 of the square root of 1 plus cosine of root t. So there's a multiple choice question somewhere in the archive where, like, to do each individual integral, like the integrals were like, 0 to like 10,000, and then also like 0 to 9,999. And it's like the calculator would overflow error on both individual integrals. But if you just went from 9,999 to 10,000, calculator would give you an answer. So it's always a good idea to look at these and see if you can simplify them first, because often they're written in such a way that they will screw with your calculator. We don't want to fall for that, basically. So let's go to the calculator. And this is where recently my videos have been not so great. So I don't know, maybe by the time you're watching this, there'll be an update. It's definitely the Inspire software that's messing it up. And that's not my favorite thing, because the Inspire software is pretty much my favorite thing. So hopefully they update that. All right, let's say f of x is. So I'm just going to punch it in, use the template here. The integral from 0 to x square root. So you can use the template. Control x squared gives you the template for the square root of 1 plus cosine of the square root of x, and then, oh no, t, dummy variable, and then dt. So press enter, look at it, see if it matches what's on the page. If it does, we just need to find. So you can do two things here. You can do f of 3 minus f of 1 over 3 minus 1. Or you could type in what we did, which was, I'm going to not use the template. I'm just going to go for it. 1 plus cosine of square root of t. Ooh, a lot going on. I think out here, t goes from what did we say? 1 to 3 and divide by 2. So that's a way to check and see if, like, notice here, this is kind of interesting actually. This one didn't give me any kind of warning. And what about this? Result obtained using approximate arithmetic. That error, man, it shows up every once. There's nothing you can do about it. And it's, in my experience, never wrong when it gives you that warning, but it gives you the warning, which makes me nervous because, like, why are you warning me? And also, what is it? I don't really know. It's got to be some computer science-y thing with like floating point decimals or something. I don't know. But anyway, I'm going to jot this down and then switch back also. So this is approximately 1.076, 1.076. So you definitely 3 decimals all the time, unless otherwise stated. So occasionally they'll say like to the nearest gallon, to the nearest person, you know, like to the nearest car, whatever. But unless stipulated, 3 decimal places. So 1.076 is our approximate value for the average rate of change. All right, find all values of C guaranteed by the mean value theorem applied to f of x on the interval from 1 to 3. All right, what do we need to be true to use the mean value theorem? So you always have to go through this process. So I need the function to be continuous on the closed interval from 1 to 3, because 1 to 3 is our interval. Continuous on the closed interval, differentiable on the open interval. So since it says find the values, it doesn't say like, does it apply? We pretty much know that it applies. So I'm just going to write down that f of x is continuous on the closed interval and differentiable on the open interval. So 1 to 3. Okay, so therefore, by the mean value theorem, f prime of c equals f of 3 minus f of 1 over 3 minus 1 for some c, maybe more than 1, but for at least some c, that's an element of the open interval. Okay, that's kind of like all the work that we've done. Now, we're just going to use a calculator on this, I think. So we could, like, you could find the derivative using the second fundamental theorem. Like, maybe let me do that just to, like, be a little clearer, right? So our function's up there in the top left corner. So f prime of x is going to be the integrand with every t replaced with the upper bound, which is x. So square root of 1 plus the cosine of the square root of x. And then times 1. So I'm going to write it. So that's involved, but I'm going to let the calculator do all the work. Well, maybe. We'll see. So let's see. We're going to solve this thing. So back to the calculator. And fortunately, we already defined f of x. See, so there's no simple antiderivative to that. There may be no antiderivative. I can't think of how I would write a series for that offhand. So the calculator just returns the integral. When it can't do it, that's what it does, which can be really frustrating. Like if you think the calculator is about to integrate something and then it doesn't, so annoying. So let's see if we can do this. We want to solve. So menu 3.1, the derivative. So, and we could just type in the derivative, which for like calculator crashing reasons might be easier, but I'm not going to do it, is equal to, and we said f of 3 minus f of 1 over 3 minus 1. Or we could have pasted down the answer, but like, why not do this? We'll see why not if this thing crashes. So I'm just going to do enter. I'm going to press Control Enter just in case. And it gives it, oh boy. Well, oh, because of the cosine. Let's try this. Let's try limiting it. So I'm going to do such that control equals 1 to the left, 1, and then control equals less than x, control equals less than 3. And do Control Enter again. It didn't really work. I mean, it kind of did. Like I get 1.9928, and that's true, or 1.9928, and this thing is true. So I'm thinking 1.9928, so 1.993, but I don't like that. So what I'm going to do instead is I'm going to go to a graph page. All right, so I need to graph the derivative. So let's do that with respect to x of f of x. Okay, and then I also need to graph the average rate of change. So f of 3 minus f of 1 over 3 minus 1. and we get this. And now I just need to find this intersection point, which hopefully works. Let's see, menu 814, click here, click. I would love to click here. Oh, there we go, click there. And so we do get that. So we get 1.993. So what happened there is, so I'm gonna write, let me just write in the notes. Therefore, C is approximately 1.993. Okay, that's the only value on the interval from 1 to 3 for which it works. What happened is that, what was I even talking about? I don't really know. Oh yeah, so the thing that happened was when you use solve and you get these weird things, to me that always just means go to the graph page, because the graph page will show you all the solutions and then you can focus in on finding the intersection points. Here, I'm just using solve. I have no like graphical insight into how many answers there should be, what they should look like, whatever. When you get that kind of warning or you get these weird like generalizations, go to the graph page and use the graph. So let's go back and see what else we have to do in this problem. Going back. So, whoops, there we go. Perhaps. So you can see I've written down C is approximately 1.993. It's kind of weird that, you know, like you're often asked to find the value of C only really on calculator questions. It's more important that like f prime of C like exists than it is to find the value of C, which isn't, you know, that's neither here nor there about this particular question, but I just want you to know that like it's weird to find the value of C. It's more important to know that f prime of C existed. All right. Write the equation line tangent at x equals 4. Use it to estimate f of 4.1. So this continues to be kind of an annoying question based on the calculator usage. So we need to know f of 4, which will be the integral from 0 to 4. I don't really need to write this, right? Because we defined f and like we know what we're doing, but once you start, you kind of just want to finish. So that's what's happening here. So that's going to be approximately something. We need to know f prime of 4, which I'm going to let the calculator do for sure. And then we'll write our tangent line, and then we'll approximate f of, so I'm going to say tangent line. This is for when we come back to the note. So the tangent line will be here, and I will say f of 4.1 is approximately, and I will put it there. All right, so this is all set up, and now I'm just going to use calculator to find those values. I'm going to write them down to 3 decimal places, but on the calculator, I'm going to try to use as many as I can keep. So I need to know f of 4. So 4.319 is what I'm writing down. And then I need to know the derivative at 4. So derivative with respect to x of f of x such that x equals 4. Fastest way for you to do that, by the way, is menu 4.2. Menu 4.2 will like pop up the template for you and you just fill it in. It's always faster for me to type. Well, I think that. I don't know if that's actually true. 0.764 is what I'm writing down. Okay, so the tangent line that I'm going to write, I will handwrite in a second. I need to approximate f of 4.1. So what I'm going to do is I'm going to say the tangent line would be y minus f of 4 equals this slope, the quantity x minus 4. And then I'm going to solve that for y. See how many decimals it's keeping? It's keeping like a ton. And then from that, I'm going to do such that x equals 4.1. So I have my approximation. I'm going to write that in. So what is that? 4.3. Ooh, this is the worst kind of rounding. Oh, no, it's not. Okay, 4.396. So 4.396. I hate when that third decimal rounds up to like 0, basically. Like, you know, you round up to 10. So you round that up to 0. And then there's a 9, and that makes that go, and it like cascades through. That's my least favorite. So what I'm going to do is I'm going to go back to the notes and write in the tangent line just so you can see how I'm writing this. And then we're probably going to have to come back to the calculator actually to answer the next part. So we'll be back. All right, so I've written these things down to 3 decimal places. So I'm going to say that the tangent line is actually y minus 4.319 equals. So I'm just saying equals. I mean, 3 decimals is what you're supposed to round to. If you round correctly to 3, as far as the College Board is concerned, that's like an exact answer, which I know is insane. But it's what it is. So this is our tangent line. We have to use a calculator for like every part because you're not finding any of these values by hand. Now, is your approximation in the previous part an over or underestimate? So over and underestimates have to do with concavity. So we need to know, is this thing concave up or concave down? This is going to be all calculator, but we're going to look at the second derivative on the interval from 4 to 4.1, right? Not just at 4, because what if there's a point of inflection between 4 and 4.1? We need to know if there's a consistent concavity between 4 and 4.1. If there is, are we concave up, are we concave down? And then we'll go from there. So first, let's go to the calculator and find that out. So we're going to need the second derivative. So we can do two things. We could either just find the derivative of one of the derivatives that we found, or we could go straight there. So I'm going to go straight there. Use the second derivative template with respect to x of, press the var key to get f of x, and see what we get. Ugh, I don't know. I'm going to store this as like f3 of x. So colon equals, and then this answer. Now I'm going to graph that. So on a new graphing page, go there, graph, and go up, graph this. Change the window, I guess, just to make sure. Like, I'm pretty sure that it's negative, but 4 to 4.1. So it's definitely negative between it being the second derivative. So the second derivative is negative, which means the function is concave down. If the function is concave down, the tangent line is above the curve, which means we get an overestimate. So now we're going to go and we're going to write that up. So all we really got here is that the second derivative is negative, but like we weren't going to get that by hand. So we needed to switch. Here we go. So I'm going to say, since f double prime of x is less than 0 on the interval 4 to 4.1, f of x is concave down on that interval. Okay, if f of x is concave down, therefore the tangent line is above the curve. And if you find that confusing, all you got to do is draw a little picture, and I do that a lot. I have a lot of trouble with left, right, horizontal, vertical, concave up, concave down. Like I don't really know. Concave down looks like this. So draw a tangent line, and you're definitely above, right? So the tangent line is above the curve on that interval. So our estimate is an overestimate, which means that we know that f of 4.1 is less than 4.396. I'm going to risk going back to the calculator and just I just want to see if we can like do it, right? Let's see what the calculator says that f of 4.1 is. So 4.39494, and our approximation is this. So we got 4.39568. So we definitely got an overestimate. We were above it. And that's something, if you have the calculator, you should try that, right? There's no reason to like speculate. You can actually check and see. But even though you can do that, it's the calculus that justifies our solution. So you have to write down the words. You have to like think through the argument. It's not enough to actually like find it. It's like, why is it true? That's what we're really looking for, not necessarily like in this particular problem, but like in general, why would this be true? So this is my answer. I'm going to cut the video here and come back. This might have been a long video. I don't know. Come back in the next video and work on the next page. So I will see you there. And I hope you're finding these helpful.